Now we can do a similar analysis for the radial velocity. So let's recall again the definition of Oort's first constant, and then write the omega dr in terms of it. It's equal to minus 2 times a over r naught, and also omega minus omega naught is equal to 2 omega over r minus r naught. So we can write omega minus omega naught as minus 2a over r naught times r minus r naught, and also r minus r naught in terms of d and the galactic longitude. So what you have is that the tangential velocity, is equal to minus 2a. So what you have is that omega minus r naught is equal to 2a d cosine L over r naught. So the tangential velocity becomes 2a d cosine squared of L minus omega d. Now use the trigonometric identity that the cosine squared is equal to the cosine of the double angle plus 1 over 2. So this becomes 2ad cosine over 2 minus omega d. So this 2 cancels. And then you have ad times cosine of 2l plus ad minus omega d. To extract the distance. Now everything in this equation here is in terms of observable quantities except omega. But we can use again omega. But we can use again the expansion of omega around omega naught and substitute the expressions for the omega dr in r minus r naught, and realize that the second term on the right-hand side is proportional to d over r naught. And according to our approximation, this is much, much less than 1, so we can cancel this term and write omega approximately equal to omega naught. Therefore, this expression above for the tangential velocity becomes d that multiplies a cosine of 2l plus a minus omega naught. And all the quantities now are measurable or known. We can then write the tangential velocity equal to d that multiplies a cosine of 2l minus b, where b is the second Oort constant equal to a minus omega naught. B is the second Oort constant. Now for Oort constant b, if you plot the tangential velocity divided by the distance, you would have a sinusoidal with an offset. The offset is the Oort constant b, and the amplitude is the Oort constant a. So the best fit to the proper motion of the cepheids, the proper motion would give you the tangential velocity, would give you then a value of b, which is about minus 12 kilometers per second per kiloparsec. Notice also that because of the definition of the constant b, we can get from constants a and b the value of the local angular velocity. If you have a being about 15 kilometers per second per kiloparsec, and b being minus 12.4 kilometers per second per kiloparsec, and b being minus 12 kilometers per second per kiloparsec, then if you subtract one from the other, you find what the local angular velocity of the local standard of rest is, giving you a value of about 27 kilometers per second per kiloparsec. So that's in agreement with the value that we have been assuming.